And again, like I said, it has the added benefit of anybody who's not doing deep learning is shallow, right? And so you got that. You got your insult game on lock, as far as I'm concerned. So here's just the major highlights of deep learning. And the first one here is the big one. And this is the one that everyone's super excited about, and which is why a lot of competing methods don't even come close to beating deep learning now, is that oftentimes when we are analyzing a data set, right, we do something called feature engineering, right, which is a fancy term for saying I'm looking at my variables and I put them into something, I transform them in some way into reasonable values, right? So if you're looking at a baseball game and you've just got the raw stats, there are certain combinations of those variables that end up being very indicative of a pitcher's success or how good a different batter is, right? Or, I mean, you guys have encountered this in many situations where you try to fit a model with the raw data, it doesn't do very well, but then when you make the realization like, oh, if I take the ratio of these two variables, it ends up doing really well because that's a good indicator of, financial health or something like that. We've all done a lot of feature engineering. The great thing about the deep learning is that it says, your feature engineering, humans, is inferior. Give me the raw data, and I'll figure everything out, right? That's what the deep learning algorithm does. Because it has that deep architecture, it's learning really intricate combinations of raw signals to the point where, a human's approach to the feature engineering is largely irrelevant. And it's also satisfying because you're like, OK, yeah, I'll just give you the raw data set, and you go to town, right? I mean, it has to be somewhat clean. It can't be, this super noisy thing. But essentially, it takes very little upfront, cost for the researcher to do this because the deep learning algorithm is going to do better anyway, right? So that's the big reason that deep learning has been so successful. Other things, I talked about the sigmoid. They later found something called rectified linear units, or ReLUs. You'll see that term all over the place. It's this function here, and it learns a lot quickly than the sigmoid does, and it doesn't require that unsupervised pre-training that I just told you about. The major thing in 2006 did unsupervised pre-training. Well, it turns out if you use this unit, you don't really need to do that, which is really nice. And there's also something called dropout, which sounds negative, right? If somebody drops out, then that's bad, right? Presumably, unless you're like Steve Jobs or something. That's rare, right? But dropout here just says, occasionally, I'm going to throw out a neuron here or there if it's not being super helpful, so that prevents me from overfitting. So if you guys have dealt with decision trees before, there's something, the decision tree method, naming terminology is even worse than the deep learning because they've got decision trees and branches and stumps. And one thing they do is called pruning, right? When you prune your decision tree, you've got all these decisions. You basically snip different ones that aren't super helpful so that you don't overfit on your data set. You're not finding these trivial relationships, right? And so dropout is, from my cursory reading of the literature, basically the neural network deep learning version of pruning, right? You just throw out neurons. Now the training time required to do this gets much huger because you're not able to, you're not quickly overfitting the data. You're basically making it more difficult for your model to learn the relationship, but with the idea that it'll be better, in the end. It's like how adults, train their children, right? So here's some. This is your cheat sheet. I'm going to see these terms a lot if I look into a deep learning paper. Major terminology, right? And so there's a few different forms, as there are in every machine learning field. There's supervised methods, there's unsupervised methods, and then there's combinations thereof, right? And deep learning is no different. So the major ones, the ones that are getting all the show time, are the supervised learning ones. The convolutional neural network, that's mainly seen huge successes in computer vision. Also, the other thing is recurrent neural networks, and then more recently, long short-term memory, which is really good with speech recognition and language processing. And I'm going to hit these very briefly. And then actually somebody said, hey, if recurrent neural networks are very good with speech and learning text, and convolutional neural networks are good at recognizing things in images, can we combine them in some way so that like I show it an image, I show my deep learning algorithm an image, it sees it, it processes it, and then it writes what it's seeing, right? It writes some, it doesn't just classify it. It, produces some sort of label on it. And so there's very recent papers, 2014, 2015 papers, where it shows an image of, like a girl in a park throwing a frisbee or something like that, and it says, a girl plays in the park with a frisbee, right? And it never saw an image of a girl in a park with a frisbee. It saw images of frisbees. It saw images of people in parks maybe playing around, and it saw images of, girls, hanging out at home, not necessarily in a park, right? And it was able to piece those things together and produce an image, right? So it's some really cool stuff. Other things you see, and now these are kind of, they operate behind the scenes, mostly because these ones are doing the really cool stuff, and these ones are important, but they're not quite, at least from my reading, they don't seem quite as fully developed. Because supervised learning is usually easier to do when you've got labels to guide you. So now that people have, started to really churn through the supervised learning problem, I think you'll start to see a lot more work being done in unsupervised learning. But some major unsupervised methods are called deep autoencoders, deep belief networks, and something called restricted Boltzmann machines. So I'm not going to go into those too much, mostly because I don't understand them, which I think is a good enough reason not to go into. I was mainly looking at the convolutional neural networks and the recurrent neural networks because that's what everyone's talking about as far as deep learning methods go. Now, the convolutional neural networks, they're designed for data in arrays, multidimensional arrays, which is a fancy way of saying, they're designed for data that are highly correlated in space. And all I'm saying by that is if you've got an image and you look at this pixel, right? It's not just a random assortment of pixels. It's not white noise. That pixel that you're seeing there is associated with the other pixels around it, right? And if you look super closely, if you zoom in on an image super close, you might be able to recognize an edge because the pixels go from really dark to really light, and that kind of stuff, right? And so the convolutional neural networks are really designed to exploit the fact that you're not just fed in a whole bunch of IID data. You're getting fed in data that have a fundamental two-dimensional structure, or if you've got video, even a three-dimensional structure, right? And where it gets its name is it introduces different types of layers, and I'm not going to go into the details, but something called a convolutional layer detects local features from the previous layer, so it'll find like little edges of things and edges that are like edges. It does a really good job of finding where basically the pixels change a lot. And then the pooling layer might take those the little edges that the convolutional layer found and like group them together and be like, oh, this is a kind of like a circular object, right? Oh, that's the ball, or that's the frisbee, or something like that, right? And so you tend to alternate between these convolutional layers that are learning local features, and then the pooling layers kind of group them up into like things. And then there's another convolutional layer that learns from there. So it's this kind of back and forth between where you're building up this deep hierarchy of, raw, very, very fundamental features that come together, and those are themselves features of something else, right? So this is the current state of the art in object recognition and detection tasks and image processing. So much so, these are two major avenues that I found that the convolutional neural networks just blew everybody else out of the water as far as computer vision is concerned. And this top one, the 2012 Imagenet Competition, this was where convolutional neural networks really took off. The computer vision people were like, yeah, it sounds all hypey. And then the task here, this is a yearly competition. What they do is they have a data set of over 1 million images. And each of those images is associated with some sort of class, right? Like what's in the image, like a dog, or oh, that's a building, or a whole slew of possible options. And so somebody trained a deep convolutional network, and I checked it out a little bit, and they were running on GPUs, which are ridiculously fast, and their model I think took 1 or 2 weeks to train, right? So this is not like, oh, I'm gonna go grab Jimmy John's and this is gonna be done by the time I get back. These are huge endeavors, and this is with GPU computing, right? Which is already ridiculously fast. So it's kind of crazy how long these things take to train. But at the end of the day, the convolutional neural network that from this paper that they trained, they were explaining what they did, it halved the error rate of its closest competitors, right? Which is just ridiculous. You think you're reaching some sort of asymptote of how well you're able to predict these images, and then it goes through and says, oh, you got 10%, I got 5%. It was this ridiculous thing, and everyone was just kind of like, oh my gosh. And this one I thought was also really interesting. There was a competition. It was through Kaggle. It was called the 2014 Galaxy Zoo competition. And what's basically happening is there's this, and I feel like this was particularly appropriate for my talk because I'm the Hitchhiker's Guide to Deep Learning, but then there's also the Hitchhiker's Guide to the Galaxy, and so there's something with galaxies. So, this talk is deeply connected with everything else. So in this Galaxy Zoo competition, what's happening is there's something called the Sloan Digital Sky Survey, and it's basically this, these super network of telescopes that are going through and imaging parts of the galaxy, right? And they're imaging other galaxies beyond our own. So rather than just looking at star systems, they're looking at other galaxies and different superclusters and all that kind of stuff. But they've got so much of this that they need to be able to classify the different galaxies as this is a spiral galaxy, this is a bar galaxy, this is a some other type of galaxy, or this one has such and such intensity compared to this one, or it's this size, right? They need to classify these galaxies in some reasonable way. And if you don't know what you're going to learn from that, but it was a fundamental problem. So they've got all these images of galaxies, and so in this competition they had a huge set of galaxies with labels. This is a spiral galaxy, this is a bar galaxy, this is a red intensified galaxy, whatever. And the winner from that competition was Sander Dielman, and his model, he basically was inspired by the Imagenet competition. But what I think is very, very important about this is they asked him, what's your key insight? What helps you a lot? It wasn't just this vanilla, I'll just take the convolutional neural network code and run it on these images instead, right? He said he exploited invariances in the data using data augmentation. That's a fancy way for saying, he explained it in some post, like here's your image of a galaxy, right? It's circular or has some degree. What he did is he divided it up into quadrants, right? So you got 4 different spots. And then the galaxy's in the middle. So then what he did is he rotated them all around so that the upper right circular part was the galaxy, right? And he didn't think that was going to help very much, but it actually helped out a lot because, and actually it doesn't have a really good reason why it helped out a lot. But the takeaway from here is that we say, oh, you're free from feature engineering. You just pump through the raw data and you're good to go. And the takeaway here was, using a feature learning approach does not excuse you from having to get to know the data. He said, feature engineering is, quote, just happens at a higher level of abstraction. So it's never a plug and play, here's the raw data, oh my gosh, look, I'm so cool, I have really low error rate, right? You have to still get to know your data, and you have to know what the network might be able to pick up on and what it might not be able to pick up on. So I thought that was really cool because there's no free lunch. The other thing is recurrent neural networks, and so these are used for things that have sequential inputs. So like a signal, you got like a Fitbit or something like that. That would be like some sort of sequential signal because it's coming at different time intervals. Or you can think of text in a page, either what character is followed by what other character, or which words are followed by which other words. When you read through a sentence, it has an ordering to it, right? And so recurrent neural networks have been used on text processing. They've also been used on speech recognition because there's a one-dimensional, direction to the data. And the way it does this is it introduces something called a state vector into the hidden layer neurons, and that's able to remember past elements. So like it can kind of infer the meaning of a sentence, so it starts to suggest, good words that are associated with what you're talking about. But at its core, this is just your regular deep neural networks unfolded in time. So you keep revisiting the same network again and again and again with that specific state vector. But it's essentially just a network of deep neural networks going through time, right? And so, but the important part is that the state vector is able to pick up on short-term associations. And so this has seen huge success in speech recognition and natural language processing. But learning long-term dependencies, so something that you read at the beginning of the paragraph and then comes back at the end, recurrent neural networks are not super good at picking up on because it's forgotten it by that time, right? And so Schmidhuber and Hulkreiter, something like that, they developed what they called the long short-term memory, right? And so it still has some sort of short-term memory, but it also occasionally has what they call like a memory cell or a forget gate or something like that, not like deflate gate, but everyone's got all these terms for everything. But this basically stores memory of a past event eventually clears it, but like will keep it around for a while, and then if it starts to pick up association with, oh, the current words I'm looking at are heavily associated with, oh, that thing from the past, right? It can learn long-term dependencies quite well. And so there's one paper where they showed it a paragraph from Lord of the Rings, and they wanted the long short-term memory to ask a question that was relevant to the particular paragraph. And I don't know the exact details of the paragraph, but the question that the long short-term memory algorithm asked at the end of the day is, where is Frodo now? Right? And so it's kind of so it was able to pick up that there's, Frodo is a major character, and he's going somewhere, and they weren't quite clear, and that was its question, right? That it asked at the end of the day. So these are beating the recurrent neural networks strictly because of the long-term dependencies, but everyone's, people are still modifying the recurrent neural networks, and at their core, they're very similar things. And just briefly, the unsupervised learning, again, I'm not going into it because, I can only learn so much. But this is where the unsupervised learning revived the neural network research because the features that you could do pre-training on the weights, and that it alleviated the unstable gradient problem. But everyone has been super excited about supervised learning, and there's been not so much research on the unsupervised end. And so this is likely where you're going to see a whole lot more progress, because humans, they mentioned this in the deep learning review by LeCun, Hinton, and Bengio, is that humans are unsupervised learners, right? Well, it's some combination of supervised and unsupervised. It's very reinforcement learning. Like, you look at the world, right, and you figure out that there's different objects, and then somebody tells you, oh, that's this object, and then you're like, oh, that's a cabinet, right? And so when I see something like that, again, I think it's a cabinet, right? And so if you really want to take the brain analogy too far, right, brains do some clever combination of unsupervised and supervised learning, and so development of the unsupervised is very important, and this is probably what they predict is where you're going to see the next huge successes in deep learning, is that people have finally revisited the unsupervised world and are learning patterns in the data without labels to help you out. Now, you're not alone in trying to implement this stuff. People have, of course, flocked to this field to create their own deep learning architectures and all that other kind of stuff. So I'm going to, in 2 minutes, go through the greatest hits of software that people are using to implement deep learning. First off, Theano is probably the biggest one. Maybe the next one is, they tend to vie for the top two. But Theano is Python. And at its core, it's a CPU, GPU symbolic expression compiler from the University of Montreal. But who here has used Mathematica before? Anybody has? Okay. Well, in Mathematica, you can do symbolic differentiation. You can say, oh, take the derivative of this expression, right? And it's able to do it because it knows how the symbols are related and that kind of stuff. So it can learn these basically structures in your model without you explicitly stating computation, like here's where the derivative is, right? And so that's essentially what Theano is trying to accomplish. It has behind the scenes this big network, not a neural network, but it's able to, it also helps because it doesn't have to recompute things. So if it computes this such and such matrix, and then it's iterating through, and it realized that the inputs to that matrix haven't changed from the previous iteration, it's not going to recalculate it every time, right? And so it does a lot of behind the scenes handling. So you can implement deep learning stuff with straight Theano, but what a lot of people have done is they've written basically wrapper packages for Theano. And some of the major ones, there's something called Blocks and Fuel. They're supposed to work together, and they're built on top of Theano. There's something called Keras. There's something called Lasagna, which I particularly like because it's talking about the layers. And so I figure, oh, you just add another layer. It's like lasagna. And so they have actually some other packaged code that they call recipes. So like if you wanted to implement the long short-term memory, you just use the long short-term memory recipe for your lasagna. And then there's something called PyLearn2, which I've actually seen a lot of complaints about. People say it's trying to accomplish too much. Like some of these specialize and recurrent neural networks or not. People say PyLearn2 has gotten a little bloated, but I can't really speak to that too much. The other major one that people are using is something called Torch7. And it's written in a language called Lua, which I honestly hadn't heard about until I researched this, but it's basically made to be very embeddable. It's a very embeddable scripting language. So think C++. You know how C++ runs on a whole lot of devices, right? But Lua's maybe a little bit more, I don't want to say intelligent than C++, but it's a little, it's a little bit more new age language that's made to be embeddable. And so what that means is that, if you create like an app or something like that and you want to put some deep learning behind the scenes, Lua is much more amenable to that than, say, Python, because Python's, not really made to be this embeddable scripting, lightweight embeddable scripting language, right? And so you coincidentally see a lot of Torch 7 development and use at like major tech companies like Facebook and Google. And some of the names you've been seeing here, LeCun and Hinton come up a bunch. LeCun is hired at Facebook, Hinton's hired at Google, right? So there's no coincidence here, right? So Torch 7 gets a lot of use in these avenues, I think, because it's easily embeddable, and so they're consistently developing it. Other ones you'll see, there's plenty more. That's why I wrapped everybody else up in et cetera. But the other major ones I see is something called Caffe, which is written in C++ and has like Python and MATLAB wrappers to it. If you're using MATLAB, there's something called the Deep Learn Toolbox. And then, of course, kind of plug Julia. Mocha is basically, they looked at Caffe and made like the Julia implementation of it. So there's a whole lot of things you can do. It's like the Wild West right now, because everyone's still figuring things out, and some things work and other things don't work, and nobody really knows why. And so it's really exciting to read up on, and especially when you're looking at papers that are published like, July 2015, it's kind of crazy. So it's an exciting world, and there's a lot of resources, so you're not alone. So remember, don't panic. Deep learning, I think, at least in its core, is here to stay. The ability to learn from raw data versus feature engineering is not going to go away anytime soon, but I think you're going to, I personally think we're going to see that take form in many different areas, not just necessarily in a neural network fashion, but who knows? Anyway, hopefully you learned something. I sure did, reading up on all this stuff. So thank you. Does anybody have questions or comments or anything like that? Yeah.
So is most of this stuff being done by like CS people?
Yeah, there's. It's a very specific niche of people. A lot of CS people, right? Because I mean, if you're not running this thing on a GPU, and you don't have a couple years to kill, then you got a problem, right? So you need to be comfortable in the programming stuff. So CS people are heavily involved in this field, but a lot of these papers, it's not long before it's fundamental statistics concepts that are being used, right? And so I think it's a domain that could use more statisticians, but I think the biggest barrier to entry for any statistician is the programming. Like the fundamental part of this is the programming, and so if you're not doing that, then you're a little bit in trouble. Any other questions? Well, Dendi, next week, would you like to give a little plug for what you're doing?
Oh yeah, hi, I'm Dendi. Basically what I'm trying to do next week is run a real-time model on Amazon Cloud Network, so you could actually see how Caffe or Lua Torch 7 actually changes, makes images into a painting artistic style. So say you take an image of this room, and you take a Van Gogh image portrait, this room could be, painted as in a Van Gogh style. So I'm trying to do that next week.
Awesome. So yeah, make sure you come next week. Hopefully this will give you some at least term recognition. Yeah, feel free to talk to me at any time. Thanks, guys.